Hello and welcome to this Python video. In this video we're going to be using some data manipulation and analysis in Python to try correct the reading of our ESP's ADC. So we would expect the relationship between the ADC's digital readout and the voltage to be linear. So that would mean we'd think that the 4096 values our ESP can read are evenly spaced. So if we had, say, a reference voltage of 2.9 volts, then if we plug that into our ESP, that would give us a reading of 4095. And we would expect to be able to divide that 2.9 volts by 4095 to find the voltage if we had a reading of 1. But that's not quite right, because the relationship between the ADC's reading and the voltage is non-linear. So we are going to have to define a function that describes that relationship ourselves. So here we are in Python. And this video is going to be working off the previous two videos where we took many readings from our ESP on a voltage divider and where we defined a function to give us the expected voltage at each branch. So the first thing we're going to do is we are going to import the libraries that we are going to be using. So that is going to be pandas, numpy, and matplotlib. Now we're going to have to read our data in. So here our data is called delayed-data.csv. So let's open that and take a look at what that looks like. So we've got one long column of our data with the heading data, and we've got 101 readings at each level of a branch, and occasionally in our data we'll have the word line. We'll see if we can find one here, like that. So what we're going to do is load in our data to a variable. I'm just going to call it data, and we'll say pd.read CSV. We'll put the name of our file, which is delayed data.csv, and we'll index it with the heading, so that was data, just like that. And that should be our data now, so we'll take a look at that. And that's what we'd expect to see, just a big long list, essentially. So the next line looks a little bit strange. We're going to modify our current data variable. So we're going to say x for x data if x does not equal. And what this is essentially going to do is it's going to look through what we had as data. It's going to look through every point, and it's only going to keep it if it does not equal line. So that should get rid of all the lines for us. So what we'll do is we will convert this back to an array, and we'll make sure it's a float, an array of floats, just like that. And print that once again, and that's our array there. Now, if we think about how we took our data, we took 101 separate readings at the 20 different points in our voltage divider. So we want to reshape our data so that it has 20 rows, one for each branch of a voltage divider, and each of those is going to have 101 readings in it. So we are going to say data equals data dot reshape 20, 101, just like that. Run that. As always, we'll take a look at what that looks like now. So you can see we've got our first branch, second branch, third branch, and so on. And each of these is going to be 101 entities long. Now, the reason we took 101 readings is so that we can take an average of these to eliminate any noise. So we're going to create a new variable now, and we'll call it average data. And we'll say that is equal to np.median data. And then we'll say axis equals 1, because this function can do one of two things. It can either take the average of every column or every row. And we want to take it of every row because we want to have the average value in each row. So we want to have the average value for each branch. We can run that. And if we take a look at that, there we are. Now we have our average reading for each branch. So just to reiterate, our aim here is to compare the readings here with the voltage that we should be reading from our voltage divider so that we can define the relationship between them. So now we're going to use a function that we defined in the last video to get our predicted voltages from the voltage dividers. So I will copy and paste that in. So there it is, and we will copy and paste our resistances in as well. So these are the resistances that we recorded for each resistor in our voltage divider. So if we look at the length of that, we've got 20 of those, and they are going in order from the voltage in with 513, and this is a resistor closest to ground here, 520. Now we're going to create a variable called VTH, so theoretical voltage, create an empty list. We're going to create a loop with a variable I, which will go from 1 to 20, because remember, it doesn't include the last number, so this loop is only going to go up to 20. Now for each iteration of a loop, we're going to add a new item to theoretical voltage, so we'll do vth.append. We're going to append the output of voltage divider with our resistances list. The branch will be I, so that's the thing we're iterating through. So we'll go 1, 2, 3, all the way up to 20. So we'll have each different branch in order like that. And voltage in. Now, it's important that you check what your voltage in is, because it says it could be 3.3 volts, but that's often not quite accurate. But for us, it is 3.3 volts, so I'll do that just like that. And then it should be able to run that after running our function. We can run that like that. And then if we print theoretical voltages, there they are like that. Now all we have to do is plot our measurements against what we expected them to be. So we'll do plt.scatter. On the x-axis, we'll put our average data. And on the y-axis, the theoretical voltages. And that is our plot right there. And that shows the relationship between the readings on this axis and what we want the outcome to be. So this function here that we're going to fit to this line is going to describe that relationship. Now, as you can see at the end here, we have these 2 points where the ADC was maxed out. So we want to remove these two because they're not accurate and they're going to ruin the fit for the rest of the graph. So what we'll do is we'll take away the first 2 points, because remember it's going from largest to smallest. So we'll say from 2 onwards for both of these. We rerun that. We've now trimmed that off and we've got a much nicer looking plot. Now we're going to fit a polynomial to this. Even though it looks linear, it's probably not a very good fit if you try using linear, and we want to be very accurate and precise here, so it's better to use a polynomial. I'm going to do a second order one, so we'll do ABC equals np.polyfit. We'll put our x data in, which is average data from the second point onwards. We'll put our y values in, which are voltage theoretical. And we'll say our order is 2. We run that. Those are variables stored there. Print those out. And these are the values of our polynomial that we have here. Now let's quickly create a graph to test how good our fit is. So we'll create a domain using linspace. And we'll go from 0 to the maximum value in average data, which is average data 2. And we'll give a sampling rate about 10,000. And then we'll say plt.plot domain on the x-axis, and then we'll use this function to do that. We'll do a times domain squared plus b times domain plus c. And then on top of that, we can scatter just like we did before. Copy and paste that. If we take a look at that here, we can see that we've got a fairly good fit. Now, if we wanted this fit to be better, we could figure out what range we actually want to measure the voltage across. So if we're only expecting voltages between 1 and 1.5 volts, it might be better to cut just this part of the graph so we can get a better fit, so that we can more accurately measure those voltages. So now we're probably going to want to put these values into the Arduino IDE so that we can use this function to spit out our voltages when we are reading from our Arduino. So I will just copy and paste these 3 values here like this and go into Arduino IDE. So here we have a generic script, which is reading a pin and just printing the sensor value. What we're going to do is create a new variable, and we'll call that voltage. And then we'll define it here. We'll say voltage is equal to, then I'm going to paste in the values that we have here. Now, C++ can't understand exponents written in this way, so scientific notation. So we're going to have to use a function called pow, which is the power function. So here we have times 10 to the negative 8. So we're going to have to write times pow 10 to the negative 8, just like that. So we've got the first value is a thing that's being raised to the power. The second value is that power itself. So now we're also going to have to multiply this by sensor value 1 squared. So once again, we'll do pow sensor value 1 squared. And then because this is polynomial, we'll add on this. That is just going to be times sensor value 1. And then that should just be our function there like that. We'll add a semicolon on the end. Now we can open the serial monitor. You can see we're reading a sensor value and a voltage.